Welcome. We're looking at nuclear chemistry today. Nuclear chemistry study reactions take place at atomic level. Now, in terms of reactions, there's two possibilities. Either we can have an emission or a bombardment. Now, when we talk about emission, an emission is where the particles are products. What particles? We'll talk about those in a minute. Bombardment is where the particles are reacted. So let's look at the particles that are possible. Okay, first of all, the first, second, last one were the first ones discovered, alpha, beta, and gamma. We're trying to be impressive because the biologists were using Latin for their names, and so we decided to use the Greek alphabet. So the first particle discovered was alpha. We use the symbol, Greek letter alpha. What is an alpha emission? It is 2 protons and 2 neutrons. Now, if you know 2 protons and 2 neutrons, that's a nucleus of a helium atom. So today we basically express that as He4/2. Second emission, what's left? Protons, neutrons are left. Only thing we have left, the symbol there is a B for beta, and electrons, pure electrons. Remember we talked about Thomson in the cathode ray tube, the beta stream, electron stream, that was good. So how do we expect that since there's no element there? We use electron 0/-1. Now we do have a proton. We stopped using the Greek symbols because scientists decided, hey, we don't need to do that. So what is a proton? Well, a proton is a proton. Well, what nucleus has a proton is center only one. That would be hydrogen. So we express a proton emission as a hydrogen 1/1. A neutron or a neutrino, of course, is just a neutron. And since there's no particle, no element, that's just a pure neutron, we use N1/0. Now, positron, that sounds something like out of Transformers or something. Positron is a part of the same mass of an electron but having the opposite charge. So if it's same mass, we're going to use the same symbol of E, but instead of being negative, it's going to be positive, 0/-1. Remember I said alpha, beta, and gamma are the 3 particles that first discovered. Alpha symbol, beta symbol, the symbol for gamma looks like a fish on its head. All right, now what's left? There is nothing left. So pure energy from the binding energy. Binding energy is what holds the nucleus together, the protons and neutrons. When that comes apart, that's the binding energy. There is no particle there, so we use 2 squiggly lines representing gamma emission. All right, now history. A quick history. There was 3 scientists that worked together. First man, a Frenchman named Becquerel, and he worked with a husband-wife team of Henry and Pierre and Marie Curie. They were really most important because Marie was a PhD, which was very unheard of in the time. At the same time, they were doing work in Germany. A scientist named Rankine was working with X-rays, and that's the basic beginning of nuclear understanding. Of course, all these folks died because they're doing nuclear particles, and they didn't know that gave them cancer. All right, now, units of radiation. The main units of radiation we're going to look with sounds like something coming out of a skateboarder. They're rads. So whenever we deal with radiation, we're dealing with units of rads. All right, awesome. Couple additional terms we make sure I understand. Isotope. Isotope we've talked about before. Isotope is a substance the same number of protons but a different number of neutrons. When we talked about that, when we talked about abundance at the beginning of the year. Radiation. Radiation is defined as the particles that release from substances at atomic level. So the particles themselves are called radiation. Radioactive is the material that releases. So radiation is the particles, radioactive is the material, and decay is the process of releasing radiation breakdown at atomic level. Make sure it's over there a little better. There we go. All right, now transmutation. We talked about the particles. This is where we're going to do this, and this is going to be the extended way of left in the lesson. So transmutation of expressing nuclear change in a reaction form. So what we're doing here is we're going to take the atomic mass, A, and atomic number, and they have to be equal on both sides of the reaction. Now, most of chemistry is pretty generic in my standards. This reaction right here, this is called carbon dating. And there's 2 standards to deal with just this reaction. So let's look at this. 14. What number are we going to add to 14 to get 14? Well, 0. So we either have a electron, a beta emission, or a positron. Well, look at the number 7. What am I going to add 7? They get 6. That number would be -1. So this would be here. This would be a beta and this would be an emission since it's on the product side. If it had been on the reactant side, it'd be bombardment. All right, let's look at the next one. I'm going to do one of these, and we'll do the next during class. So if we look at 35, what do we add to 35 to get 36? 1. What do we add to 80 to get 81? 1. Which one's 1 over 1? H. So we named this. This would be a proton emission. Okay, again, we'll do those other 3 in class. All right, now we can also do what's called a transmutational series. Okay, so we're going to run through each one, and I'll do this in class, but the product here is going to become the reactant over here, and so on and so on and so forth. Now, in most cases, this will continue until we hit lead. Most radioactive series do end up at lead. I don't be thinking that's always the case. I will give you ones that don't end at lead just so that you don't get cocky and think you just put down lead as the answer. All right, now we'll do those 2 at the end of class. Any questions, let me know. With that, we're done. Take care, be good.